and I've got audio and recording, and looks like this is another one of those days where I'm going to be recording this lecture to an empty room. We'll see how this works. I will tell you again that this is an incredibly awkward exercise to go through, so you get what you get. Last time we talked about the normal distribution. Now, I want to try and give this some application for you. One of the examples they work with in the book is the idea of you go to the doctor and the doctor says your blood pressure is normal. Well, we all have a rather intuitive notion of what that means. But what does it really mean? It means that in the medical profession, they have aggregated enough data on the blood pressure of people in general that they have a good idea of how those blood pressures are distributed in the population. And that it is a normal distribution. The mean and standard deviations. And if you look in a normal distribution and you measure the standard deviation, you're going to find out that about 95% of all the population is going to be within those two boundaries, plus or minus 2 standard deviations. Now, in the case of blood pressure, it means oh, looky here, yay, I'm not going to be talking to myself for an hour after all. And I will actually even start over. Oh, that's okay. Believe me, I'm quite pleased to do so. I really hate trying to lecture to an empty room. I was revisiting normal distributions from last time. And the idea is to give you some application. Not just, it's all well and good to look at the theory, but how is that theory applied? And the example I was talking about, one of the examples they use in the book, is when you go to the doctor and the doctor measures your blood pressure. He says your blood pressure is normal. Well, what does that mean? We have a colloquial kind of intuitive understanding of what normal means. But technically, what it actually means is that the medical profession they've taken enough data, they've looked at enough data that they know we now know what the distribution of blood pressures are among adult human beings. And it is a normal distribution. It is bell-shaped, symmetrical, about the average, about the mean. And if you look at the interval from minus 2 standard deviations to plus 2 standard deviations of that distribution, you're going to find that 95% of the population falls within those two limits. So when the doctor is telling you your blood pressure is normal, I think in the case of blood pressure, it's systolic. It's systolic over diastolic, and the systolic from 110 to 130 is normal. 110 to 140 is normal. Yeah, I think 130 they consider pre-hypertensive. 140 and up is hypertensive. Well, what that means is just that. And don't quote me on these numbers, but basically it means something to the effect of this 2 standard deviations below the mean, you're at 110 systolic, and 2 standard deviations above the mean, you're at 140. So that's what, 30? So that would put 125 at the mean? Yeah, okay. That's what it means when the doctor says your blood pressure is normal. It means you're within a couple of standard deviations of the mean of the population. And then they use that information to know that, okay, well, if your blood pressure is outside this range, then we need to take steps to correct that. That's a whole nother subject for a whole nother school. I do want to revisit this just to make sure that it's clear. We have this, we talked about the difference between descriptive and inferential statistics. Well, we take two normal distributions. One looks like that, as a mean of mu sub 1, and standard deviations like so. Okay, that's one distribution for one set of data. Now, if we take a different set of data, its distribution might look like this. Where it has mu sub 2 and sigma sub 2. Okay? Well, at that point, it's kind of hard to compare this distribution to that distribution, so we came up with what? Z-score, exactly. The Z-score tells you how many standard deviations you are from the mean for any given datum. Right? Well, that gives us the notion of the standard normal distribution. The standard normal distribution is also a distribution, a normal distribution, but one whose mean, by definition, is equal to 0. And whose standard deviation is equal to 1. Right? That is the standard normal distribution. So, if you have a specific normal distribution with a mean that's not 0 and a standard deviation that's not 1, how do you analyze it? Well, you could do it. What was that equation? Probability of x is equal to e to the minus x minus mu squared over 2 sigma squared divided by, I don't remember, 2 pi, something, square root of 2 pi, something or other. Okay, the point is we've got Gauss's equation. normalized, we could analyze any of these distributions directly using that equation. We want to know, from any value of x, what percentage of that distribution is above or below that value of x. So where in the distribution does that value of x fall? Well, we could take that x and plug it in and do the integration from minus infinity to x and get the percentage and so forth. Or, and quite frankly, nowadays with computers, we got wristwatches now that could do the math as fast as you could type in the numbers. But before we invented these super fast portable computers, they invented this instead, the standard normal distribution. So if you have this specific normal distribution, and you want to know what percentage of the population is above or below a particular value of x, you just turn that value of x into a z-score and look it up on the standard normal distribution. That's the table. Did you find your foldout, by the way? So you find, well, at any rate, you find the table's also in the back of your book, table E, and it's the standard normal distribution. And it gives you values of z from minus 3.4 to plus 3.4. Or is it 4.9? No, just 4. Okay? So, if you want to know what percentage of the distribution is below a score, a z-score of minus 2, you get out your handy-dandy table, you find minus 2, now what's the rest of your z-score? You might turn to the back of your book so you can follow. Oh, you did. Good. So you can follow along. Let's say we want to know in this distribution everything from this x on. And everything from that x to here. Well, we say at that x, the z-score equals, you calculate that x, and say it comes out to 2.003. Okay? You come over here, you find your handy-dandy table, you look up minus 2.0. Then you move over to the column that ends in 0.03, and there you have a number, 0.0212. That is the probability that a given member of this population will be less than a z of minus 2.03. Okay? Stated differently, that means that 2.1% of the population is below 2.03. It's somewhere in that shaded area. Okay. Let's do a quick experiment here. Let's look up the score for minus 2.0. And that gives us a score, a distribution, a probability of 0.0228. Now, what if we go and look up the z of 2.0? That tells us, that gives us .97 what? 72. Okay? So, that means that from here, we've got 2.28% of the total population is from here back. We come over here, and we find that 97.72% of the population is from there back. So what does that mean? What does that tell us about the percent of the population here, between these two limits? Well, if all of this is 97.72%, and from here on is 2.28%, then everything from here to here will be 97.72 minus 2.28 equals what? Equals 95.44%. Remember a while ago we said that everything between here is about 95%? Well, that's a more accurate or more precise number of what that is. Look at what about plus to minus 3? If we go to minus 3, we find our probability of less than 3 is 0.0013. Get that right? Yep. And plus 3 would be 0.9987. So what's the percentage of the population between z of 3 and z of minus 3? 0.9987 minus 0.13 would be 0.9974. Stated differently, because what does that z-score of 3 mean? That means you're 3 standard deviations above the mean, 3 standard deviations behind the mean. This tells us that 99.74% of a normally distributed population will be between plus or minus 3 standard deviations of the mean. Okay? This is how you use those tables. And why you don't have to worry about memorizing that equation, Gauss's equation. It also means that you can make comparisons between distributions. Even if one distribution has a mean of 6 and a standard deviation of 0.13, where another distribution has a mean of 14 and a standard deviation of 12. You can convert them into, as long as they are normally distributed, you can just simply convert your x values into z-scores and look them up on a standard table, standard normal distribution table. Table E in the back of your book. And they give some examples here in 6.1 of how to look up, how to make application of these. I'm sorry, I said 6.1. Well, they do give you some examples in 6.1, and then they go through and do more application examples in 6.2. Let's go ahead and do this. Let's look at this one example just for completion's sake. We'll say example 6.6. They look at how many liters of blood does an average person have? They say that on average, a human adult has 5.2 liters of blood. Now, because this is a probability distribution, we can say that that mean of 5.2 liters is the expectation value. That if you don't know anything else, you know that's what you expect the value to be. That's the most probable value. But it has a standard deviation of 0.3. Okay? So, the mean plus 1 standard deviation would be 5.5 liters. Plus 2 standard deviations would be 5.8 liters. Plus 3 standard deviations would be 6.1 liters. Minus 1 standard deviation would be 4.9 liters. Minus 2 standard deviations would be 4.6 liters. And minus 3 standard deviations would be 4.3 liters. That means, right off the bat, we know that 99.47, something like that, percent of the population is going to have between 4.3 and 6.1 liters of blood in their system at any point in time. Or that's going to be their normal amount of blood their system produces and maintains. So, what the question asked in the example is, what percentage of people have less than 5.4 liters of blood in their system? So, all right, well, let's draw our distribution curve. Now, where's 5.4? About right here. Okay, what's the Z of 5.4? Liters of blood on this particular distribution. That's a Z-score of 5.4 minus 5.2 divided by 0.3. The value minus the mean divided by the standard deviation. .67. Okay. Well, if Z equals 0.67, that's a positive 0.67. That means that someone with 5.4 liters of blood is 0.67 standard deviations above the mean. Okay? So let's look up 0.67. on our table E, and then slide over to 0.07 for 0.67, and what number do you get? .67. So you find plus 0.6 and then move over to the 07 column. There you go. So is the probability that any person, any member of this distribution would be less than 5.4, or stated differently, 74.86% of the population has less than 5.4 liters of blood in their system. See how that table works, right? Okay. Now, I'm going to go through something called the central limit theorem. Because, let me ask you, how do we know that the average, the mean of the entire population of the human race, the mean systolic blood pressure is 125, whatever those are, millimeters of mercury or whatever? Did we go and measure every adult human being's blood pressure? No. But we are confident that the actual mean of the entire population, if we could go and measure every adult's blood pressure, we're confident that the mean would be 125 millimeters of mercury. How? Central limit theorem. We talked about how we can use samples to approximate the population. And that's, in fact, the difference between a parameter and a statistic. If it's talking about the whole population, it's a parameter. A mean of 125 millimeters of mercury is a parameter, not a statistic. So, if we take a sample of, say, 30 adults and measure their blood pressure, what is the mean of that sample going to be? It's going to not be 125 millimeters of mercury. It's going to be a little less than that, or a little more than that, but it's not going to be that, because we only dealt with a sample. And the sample is never going to exactly reflect, the statistic will never be exactly equal to the parameter. In the case of the mean, it can be a little above, it can be a little below. But what if we then measured another random sampling of 30 adults and took the mean of that sample? And then we did another sample of 30 adults and took the mean of that sample. and did another sample of another 30 adults and did the mean of that sample and did that 100 times, we could then have a frequency distribution of 100 samples of the means of those samples. And we would find that those samples would form a probability distribution, or would form a distribution that would become a normal distribution. And the mean of that distribution would be equal to the mean of the population. In other words, let me just read it. The mean of the sample means will be the same as the population mean. That's the central limit theorem, that if you can get to the mean by the mean of the population by looking at the limit of where the samples, the population distribution of the samples tend to go. They will tend towards that central limit of the mean of the population, of the actual parameter. A sampling distribution of sample means is a distribution using the means computed from all possible random samples of a specific size taken from a population. Now, that's an important point. It says that the sampling distribution, in order for the central limit theorem to hold in exactly, is that that must include all possible random samples. Okay? And if it does, then it is a mathematically provable certainty that this is where it will go to. In practice, you can just look at where this what value this approaches asymptotically, and that will give you in the limit of where that approaches, that's where that will be your mean, the parameter, the mean of the population. Again, they point out the sampling error as opposed to what other kind of error? The sample error as opposed to what other kind of error? Non-sampling error. Yeah. The sample error is not, because it is not the researcher imposing their prejudices. The sampling error is the unavoidable error that arises because the statistic will never exactly equal the parameter. Okay? The sampling error is what will average out in the central limit. It's what will disappear if you take every possible random sample of a given size. What about the standard deviation? The standard deviation of the sample means will be less than the standard deviation of the population. What it will be equal to is, let's see, the standard deviation of the means will be equal to the standard deviation of the population, the parameter. In fact, let me rewrite this. I'm not sure how they write it in the book, but I'm going to try and make the distinction between the statistics and the parameters. The standard deviation of the means will be equal to the standard deviation of the population divided by the square root of the sample size. Remember, in order to do a sample distribution of the means, it has to be all of the samples have to be the same size. They worked through a very, very simple example here where they demonstrate how this works. They give us a, well, let's go ahead and do it. Let's say that they say the mean of a, to demonstrate the example, to illustrate, thank you, that's the word I was looking for, to illustrate what we're talking about. Let's use this example. Suppose a professor gives an 8-point quiz to a small class of 4 students. The results of the quiz were 2, 6, 4, and 8. Okay? It's an 8-point quiz, and he gives it to 4 students. And the scores are 2, 4, 6, and 8. So, what's the mean of this population? Because this is a population. Remember, population doesn't have to be huge. It just has to be every possible member. Okay? So what's the mean of this? 2 plus 4 is 6, plus 6 is 12, plus 8 is 20. 20 divided by 4 equals 5. That's our, oh, I hope I got that right. Yes. That's the mean of the population. That is the actual parameter. What's the standard deviation? Now this one I'm going to copy out of the book. The standard deviation of the population is (2 minus 5 squared plus 4 minus 5 squared plus 6 minus 5 squared plus 8 minus 5 squared, all divided by 4. Minus 5 is -3 squared is 9. Plus 4 minus 5 is -1 squared is 1. Plus 6 minus 5 is +1 squared is 1. Plus 8 minus 5 is 3 squared equals 9. So we've got 9, 18, 19, 20 divided by 4. Equals the square root of 5 equals 2.24. Okay, they said 236. These are the actual parameters. It's 5, 2.236 is the standard deviation. So, now let's demonstrate the central limit theorem. If we take every possible 2-member sample of this population with replacement. Okay, so you have to, when you take a sample, you replace it, and then you take again. Every possible one would be 2 and 2, 2, 4, 2, 6, 2, 8, 4, 2, 4, 4, 4, 6, 4, 8, 6, 2, 6, 4, 6, 6, 6, 8, 8, 2, 8, 4, 8, 6, and 8, 8. You know, I want to point something out here. Here we have 2 and 4. Here we have 4 and 2. Those are two separate samples. The total, what does that tell you is the total number of possible samples of a given size in any population. Total number of samples of n size from a population of, from a population of m members is MPN. The total number of permutations of n size from a population of m. In this case, there are what? 4 members, and it's 2, so this is 4p2 would be 4 factorial divided by 4 minus 2 equals 2 factorial. Is that right? Or do I have to? I'm not sure if I'm remembering the formula correctly. Let's see. Nine over the m factorial over m minus n factorial. So 4 factorial is what, 24? Divided by 2 should be 12. And that's actually 16, isn't it? That's an interesting little observation. Why is that? This seems to me like this would be the number of permutations. Why is this giving us 12 instead of 16? Oh, I know why. Because this is why it says with replacement. That is not a permutation. That is not a permutation. That is not a permutation, and that is not a permutation. We have 4 additional permutations where you have the same actual member twice. Okay. That was an interesting little observation. That's the first time I've noticed that. All right, cool. Now, if you do a frequency distribution of this, you end up with 2 of 1 let's say for x, bar of 2, you have 1. And that's what you do. You take the average of these. 2 plus 2 is 4 divided by 2 is 2. 2 plus 4 is 6 divided by 2 is 3. 2 plus 6 is 8 divided by 2 is 4. 10, this would be 5. 3, 8, 5, 6, 4, 5, 6, 7, 5, 6, 7, and 8. So you can have average of 2 through 8. 2, you get 1. 3, you get 1 and 2. 4, you get, let's see, just 1. Here's a 5. Here's an 8. Here's another 5. Here's a 6. There's another 4. There's a 5. There's a 6. There's a 7. There's a 5. There's a 6. There's a 7. And there's another 8. How did we get an 8 over here? 4 plus 4 is 16. No, 4 plus 4 is 8. I'm not 4 times 4. So that would be 8, that would be a 4. Which would give us one more here and one less here. Okay. Oh, that looks better. So we've got 1, 2, 3, 4, 3, 2, and 1. If we take the mean of these, what do we have? All of them added together, we get 2 plus 3 plus 4 plus 5 plus 3 plus 4 plus 5 plus 6 plus 4 plus 5 plus 6 plus 7 plus 5 plus 6 plus 7 plus 8 equals 80. Divide by, what did we say, 16? Looky there. The mean of the means is equal to 5. Exactly what the original population mean was. They also go through and do the standard deviation, and it works out to be exactly equal to 2.236 divided by the square root of the sample size of 2. So you divide 2.326 by the square root of 2, and you'll get exactly what you would get if you calculated the standard deviation of this. That is the central limit theorem. And that's how, it's not something you're going to do in an afternoon, but over months or years of collecting data and analyzing people's blood pressure measurements and such, and judiciously throwing out outliers. But you can, in fact, come up with the actual parameters of the population. And that brings us to the last topic under continuous probability distributions. That is the normal approximation to the binomial distribution. That may seem like, well, we're going backwards, right? We looked at the binomial distribution and extended that to the continuous. But it really isn't. The fact is that standard normal distribution table is a mighty handy thing to have and to use. But what if the population that you're trying to evaluate is not a continuous population? What if it is, in fact, a binomial distribution that you're trying to analyze? Here is your normal, standard distribution. But if you're dealing with a binomial distribution, you do not have continuous, you don't have continuous values of x. You have discrete windows of x, like so. Right? So, what if you're dealing with this value of x here? Well, if you are dealing with continuous distribution, you have exactly that value. And you know that from that value on down, this is how many, you turn that value into a z-score, and you look it up and you find out that from this point, all the way back here, P percentage of the total distribution population will be below that value, right? And that's the key. That's what you do when you look up a table, when you use this table. If you want to know what percentage is above that value, you look up the value on the table, and then you subtract it from 1, and that tells you what's everything that's on the other side. Okay? If you want to know what's between two values, you look up those, you turn them both into z-scores, and you look at the percentage, you subtract everything below and everything above, and take just what's left in the middle. But if your actual population is not a continuous population, but a binomial distribution, then you need to make a correction here. So you would say, if you're looking for the probability of x less than z, some number, let's not use z, let's say x less than n, then you would look up the z value for n, but then you would add the, remember the boundaries in a discrete distribution? Remember how we added the boundaries, where you take the value x minus 0.5 and plus 0.5? Okay, well here you have boundaries. So you take, instead of x, you have, instead of x equals, I'm going to just use a number 3. You have 3 minus 0.5, and 3 plus 0.5. And that becomes your boundary. Your boundaries for this. Okay, now if you want to know, now you can take and look up the z-score for 2.5 and then the z-score for 3.5 and take the difference, and you've gotten this total area right here. You've got the total probability for that particular class or bin or group. Okay? What if you want to know what's less than this? If you're looking for the probability of members being less than that, well, then you would look, instead of for probability of something less than 3, you would instead look for the probability of something less than 2.5. Okay? You're saying, because if it's more than 2.5, if it's 2.5 or more, it's going to be part of that area. It's going to be part of the. And if you're only interested in what's less than this, then you just move down one boundary, down to the lower boundary. If you want to know what's above that point, now that's if you want to know what's less than. What if you want to know what's less than or equal to 3? Instead of p less than 3, you've got p less than or equal to 3. Well, then you say, if it's at this upper boundary, if it's at the positive boundary, 3.5, it's still part of 3. So you would change that to probability of less than or equal to 3.5, the upper boundary. But if you want to know if you're looking for the probability of greater than 3, well, then you look for the probability of greater than 3.5. But if you're looking for the probability of greater than or equal to 3, then you look for the probability of greater than or equal to 2.5, the lower boundary, so as to include anything that would be in 3. And that in a nutshell is how you make corrections to use the table E, to use the standard normal distribution to approximate a binomial distribution. And they give you some examples here to work through. And we're out of class time, so. But I think, do you have any questions? Anything I've covered that just didn't make sense? Okay, well, if you understood what I've covered, then you should be in good shape just reading the book, reading through the examples. And if you're not, then you've got my email address and you know where my office is. All right. Oh, you did? Oh, over at the assessment center last. Excellent.